All right, 171 class, this is our third part of our notes on section 2.3, and now we're going to talk about zeros of polynomial functions. All right, we talked a little bit about this in the last section, but we didn't really get into great detail about how they're found or really even what they are. The zeros of a function are the values of x, the input, that make f of x, or the output, 0. Okay, so you plug these numbers in to the function. So I replace x in this function with some number, and if after I cube it and square it, multiply it by 3, add those, subtract the number, and subtract 3, I get 0, then that number that I plugged in that caused that to happen is called a 0 of the function. Okay, sometimes they're called the roots or the solutions of the equation f of x equals 0. And graphically, they're the x-intercept. Okay, so if it's real, that is, if it's a real number, it's an x-intercept. All right, so if I want to find all the zeros, what I do is I set the polynomial function equal to 0, and then I just use techniques that hopefully you've learned before to find these things. If you don't know how to solve the polynomial equation by factoring, you need to check out the chapter P for our book, which is the P means prerequisites. It means things that you should already know how to do coming into this class. So if you can't factor this and solve it, if you don't understand the techniques, then you need to go back and revisit that chapter. All right, if I have 4-term polynomial, 4 terms means grouping is the technique you would use. So I'm going to factor this thing by group. Okay, so if you remember how grouping works, what I'm going to do is I'm going to make these 2 terms a group, and I'm going to make these 2 terms a group. And I'm going to separate those with addition, meaning I'm going to say, all right, x cubed plus 3x squared, your group, plus negative x minus 3, your group. All right, and if you add these 2 things together, you're right back to where you started. So no harm done in grouping these together. Now when you use grouping, after you have your 2 groups, you find the GCF for each group. Right, the GCF here equals x squared. Right, the GCF here, there really isn't one. You were probably taught when you learned to factor that if the greatest common factor is 1, then you don't do anything. That's not the case with grouping. If the greatest common factor is 1, or in this case negative 1, you factor it out. Now, I'm saying negative 1 because the leading coefficient in this little group is negative. So I'm going to pull out the negative. But also, the only thing that divides x and 3 is 1. So I'm going to pull it out as well. Okay, so pulling out the GCF here, I get x squared. And then that will leave me with x cubed divided by x squared is just x. 3x squared divided by x squared is just 3. And then here, I'm going to pull out a negative 1, so I'm going to write it this way. And then negative x divided by negative 1 is positive x. Negative 3 divided by negative 1 is positive 3. If you remember, when you use grouping, you want the same thing in the parentheses here. Alright, now, because this is the same, I can literally factor it out. So x plus 3 comes out, and I'm left with the x squared and the minus 1. So you're factoring this out. These are being multiplied by x squared and minus 1. So when I pull it out, I'm literally doing the same thing as I did here. I'm pulling out negative 1, and I'm putting the negative 1 out here. I'm pulling out x squared, pulling that out in front of the parentheses. So here I'm taking x plus 3, and I'm putting it out in front of the parentheses, and what was left over is x squared and minus 1. So we've created a factored form. That's the whole purpose of this. We've factored this polynomial by grouping. And this is a difference of squares that can be factored further. So x squared minus 1, I can write that as x minus 1 times x plus 1. Again, if you don't remember any of these factoring techniques, go back and review chapter P. Alright, x plus 3, x minus 1, x plus 1, all those multiplied together equals 0. So now I set each factor equal to 0 and solve. So x plus 3 could have been 0, x minus 1 could have been 0, or x plus 1 could have been 0. Alright, subtracting 3, that leaves me with x was equal to negative 3, adding 1, x was equal to positive 1, subtracting 1, x was equal to negative 1. Alright, so there are the zeros of this polynomial. Alright, now notice it was degree 3. So because it's degree 3, the maximum number of zeros is 3, and we got all 3 of them right there. Okay, and what it says here is that each real root of the polynomial is an x-intercept. So all 3 of these are real, so if I plug this function into the calculator, zoom 6 to get to the standard window, negative 3, negative 1, 2, 3, there's negative 3, negative 1 right there, and positive 1 is right there. So each one of those numbers is a 0. So trace negative 3, I can see that makes y 0, negative 1, that makes y 0, and then positive 1 makes y 0. Okay, another really cool thing that you're going to use a lot in this chapter is the table. So if I press second graph, that takes me to the table, and I can see right there negative 3 makes y equals 0, negative 1 makes y equals 0, and 1 makes y equals 0. So I can see the zeros of the polynomial underneath the table feature by looking over in the table from what makes y equals 0. There's a 0 under y, so that means x is a 0 of the function. There's a 0 under y, so negative 1 is a 0 of the function. There's a 0 under y, so 1 is a 0 of the function. Okay, now don't confuse that with there's a 0 right there, so negative 3 is a 0. Okay, this is what we call the y-intercept, right? That's where it crosses the y-axis. So remember, if you're using the table, it's the zeros under y are what you're looking for, and the x's that correspond to those. Alright, let's practice factoring again. Find all the zeros of this function. So set the function to 0. Alright, and now you go through your factoring techniques. So this thing right here, the first thing you should always try is removing a GCF. So the GCF here is x squared, right? And because the leading coefficient is negative, I'm going to pull out a negative x squared. Alright, so a negative divided by negative is a positive. X to the 4th divided by x squared is x squared. Positive divided by negative is a negative. 4x cubed divided by x squared is just 4x. Alright, and then a negative divided by negative is a positive. 4x squared divided by x squared is just 4. Alright, and then I've got a negative x squared. This can be factored further. X squared, so I'm going to have an x and an x, a positive 4. And then they have to sum to negative 4, so that's going to be a minus 2. Minus 2. Okay, now so technically that's it, but because this is the same thing, I'm going to write it as negative x squared and then x minus 2 squared. Alright, so what are our zeros? I set each of these factors equal to 0. So negative x squared equals 0. And then x minus 2 squared is equal to 0. So if I take this negative and divide both sides by negative 1, I just get x squared equals 0. And then take the square root of both sides, I would get technically x equals plus and minus 0, but 0 doesn't have a sign. So x equals 0. Same thing here, if I take the square root of both sides, I get x minus 2 equals technically again plus and minus 0, which would still just be 0. And then add the 2 over, I get x equals 2. So the zeros of this thing are x equals 0 and x equals 2. Alright, so this is our polynomial. I'm going to press zoom 6 to graph it, make sure we're in the standard window, -10 to +10. And this is what I end up seeing. So 0 was a 0, so there's 0. 2 is a 0, so there's 2. And what I want you to get in the habit of when you see this, if you haven't already done the work, if you're just graphing the polynomial and you see this, you need to really get in the habit of either tightening up your windows, like zooming in, changing your window to only look at a few numbers. So if I'm going to come in here and tighten this up, I'm going to go from -1 to x for x up to 3, 4. So I'm going to change this from -1 to 4, and then I'm going to tighten this up to -5 to like 2, just to make sure that I am seeing what it looks like I was seeing, meaning that it does just go up just a touch right there, come down and touch again. You can also just press zoom, option 2 to zoom in, and then just pick an area to zoom in on. So even though I've already zoomed in, I'm convinced that it's just going up there and touching. If you want to convince yourself even further, you just keep zooming in, and you can see that yeah, it does just go up and touch there at the x-axis and go back down. Alright, zoom 6 gets us back to the standard window. So if this thing does just go up, touch the x-axis at the origin, come back down, and then touch when x is equal to 2 on the x-axis, and then go back down. Now, the reason that's happening is right here. So what this says here is, notice when we got to there, that each factor occurred twice. That's why I chose to write x minus 2 times x minus 2 is x minus 2 squared. Each factor occurs twice, and I know that from these powers. So if the same factor, x minus r, like x minus 2, occurs k times, like that would be the k in this case, but not k plus 1 times, okay? So it's not occurring 3 times, or we don't have it written over here another time. Then r, which would be, again, the 2 right here, is a 0 with multiplicity k, right? So we say that this previous function that we had has x equals 0 is a 0 of multiplicity 2, right? Because I could write this as negative x minus 0 squared, okay? X minus 0 is just x, right? And so that's x squared. So that would be x minus r, x minus 0. R is a 0 with multiplicity k. 0 has multiplicity 2. Okay, same thing with x minus 2. So I could also say x equals 2 is a 0 with multiplicity 2. They both are. They're zeros with multiplicity 2. Alright, the previous example we did, when we got to here, when we got to the factored form, everything was raised to the first power. So x plus 3 to the first had a 0 of x minus 3. That would be multiplicity 1. So with this one, so all 3 of these zeros had multiplicity 1, because they're all being raised to the first power. But the one that we did here, these were being raised to the second power. So the things that make these factored pieces equal to 0, which was 0 and 2, were multiplicity 2. Alright, and notice this polynomial was degree 4. This 0 was multiplicity 2. This 0 was multiplicity 2. Right? And the multiplicities, if I add the two multiplicities together, I get 4, which was the degree of the polynomial, which, if they're real, okay, if the zeros are real and there's only real zeros, then the multiplicities of the zeros will add to the degree of the polynomial. Again, as long as all the zeros are x-intercepts, as long as they are real, that will happen. Alright, if a 0 is of even multiplicity, right, 2 is even multiplicity, and the graph touches the x-axis and turns around. It touches the x-axis and it turns around, like we saw before. Right, goes up, touches, turns around, touches, turns around, at 0 and 2. Right, if it's odd multiplicity, the graph crosses the x-axis at r. So this is the same graph. This is what we were looking at before. I've just got it in factored form. And again, we know what it's going to look like because we've seen the graph a couple times now. But what I'm saying here is odd multiplicity. If I go and I change this x minus 2 squared here, if I change that power, which is determining the multiplicity, all right, if I change that power to an odd number, now instead of touching and turning around, it crosses. So at 0, it was still even, but at 2, I changed it to a 3, I changed it to an odd number, and it crosses. So that's what this is saying right here. If a 0 is odd multiplicity, the graph crosses at that 0. So if I change this also to a 3, an odd number, now they're both odd, so it's going to cross in both places. Right? So odd, it crossed, odd, it crossed. If I change this back to even, right, crosses, goes, and turns, and touches. So odds multiplicities cross, even multiplicities turn and touch. Alright, so here's a question that asks to put all that together. So remember x plus 1, if there's nothing written out there, remember that's a 1. So the zeros, when you have this factored form, the zeros are what makes each of the parentheses equal to 0. So if I just take what's in the parentheses and set those things equal to 0, so the stuff that's just inside these two parentheses is what I'm doing here. I'm just taking this, setting it to 0, taking this, setting it to 0, and then just doing the math. So subtract 1, x minus 1 is a 0. Add 3, 2x equals 3, divide both sides by 2, x equals 3 halves, or 1.5. Both of those are zeros of this polynomial. Okay, this came from the parentheses with an odd exponent. 1's an odd number. So that's multiplicity 1, which is odd, so it's going to cross. Alright, but this 3 halves came from this, and that came from this parentheses with an even power. That's an even multiplicity. Well, it's multiplicity 2. So because that's an even number, it's going to turn and touch. Or sorry, touch and turn. Alright, so there is the polynomial written out in my calculator. And again, I can also graph these. Zoom 6 to get back to the standard window. And there's our x equals negative 1, where it crosses. And then here, the x equals 1.5. I'm going to zoom in on it so you can see. If I go over there, it's roughly close to 1.5. So if I go over there and look, I can see that it touches and it turns around, never crosses. Alright, so you can again use your calculator to help with a lot of these things.